So let's just get started with the exam. And some questions I'm going to run through quickly. Some I'll spend a little more time on. So the first question was asking you to select data structures. First one was asking you about the data structure that allows you to efficiently determine whether a voter has already voted. So you need to be able to insert voters and find voters. And it said they don't have to be kept in sorted order. And that was important because essentially your two choices here were a hash table or a set. And because they don't have to be kept in sorted order, the hash table is more efficient because hash tables support order 1 or constant time inserts and finds, whereas sets require log-n inserts and finds. So hash tables are more efficient than sets or maps. And the only reason you use a set or a map is either because we tell you to, or because you need to keep the items in alphabetical or numeric order. So you use maps and sets when you have to keep things in sorted order. That wasn't a requirement here. Okay, second problem, you're working for Scumbag Air that double books a lot of seats, and you need to be able to store multiple seat name pairs where the seat may be a duplicate. So the fact you're storing key value pairs means you use some kind of map. And the fact that you have to have duplicate keys means you need to use a multi-map. Because multi-maps allow you to store duplicate keys. Okay. Third question, you're simulating a system with 10 elevators. They're numbered from 0 to 9. You need to be able to efficiently add the records and gain access to them. That's perfect for a vector. Okay, you're not adding or deleting after the first set of 10 records have been added. So it's a static data structure. Vectors are good for that. Vectors support constant time access. You just give it an index and it's constant time access to the record. So much better than any other data structure there. C, data structure for modeling a line at a bank is a DQ. Because DQs efficiently handle inserting and deleting at either end. In this case, you need to remove items from the front of the queue, add them to the back. A DQ supports that efficiently. The next one, you're keeping track of email messages, and the date is the key, the message is the value. Should be pretty clear that you may have multiple messages with the same date. So again, we're looking at name value pair or key value pairs. It's going to be a map or a hash table. And the question then is, we've got, they're not unique, which kind of rules out a hash table. Hash tables are generally requiring unique keys. Also, just to make it sure, I said the dates had to be stored in order, which meant it had to be a map. So that meant you needed to use a multi-map because you could have dates with the same value. So you could have keys with the same value. Now, it is possible to use a hash table with duplicate keys. Just gets a little more complicated in that case. But the real thing here was the fact that they were being stored in sorted order. Okay, next one, graphical objects often draw objects on top of each other. It's called a stacking order. And they typically use a list to maintain this stacking order because there's a lot of different operations on these objects. You can bring them to the top, which means you bring them to the end of the list. You put them at the bottom. You put them at the front of the list. You delete an object, you need to delete from the middle of the list. The objects are in no particular order, hence a list is the perfect data structure for storing them. And finally, you want to keep track of the number of times each word appears in an essay, so a frequency count. And you need to be able to keep the words in alphabetical order as well. So that rules out a hash table because we need to keep them in alphabetical order. Without the specification of alphabetical order, we would use a hash table. It would be more efficient since it supports order 1 lookups and insert. But because we need to keep the words in sorted order, we'll use a map. And in this case, the words are unique because you're simply keeping a count for the second, for their value. Okay, so this is something you're going to have to get comfortable with in your careers, is choosing the right data structure for solving a problem. Sometimes you have multiple data structures at your disposal, but some are more efficient than others. And you need to be aware of their characteristics, be able to select the most efficient one given the constraints of the problem. Okay, so that's what 1 was testing. 2 was testing your knowledge of pointer variables. And most people got this right, so I'm actually not going to go over it. If you got it wrong and aren't sure about it, feel free to ask me after class, but this was generally correct for most people. Number 3, the definitions. So you get a seg fault when you attempt to dereference through a null pointer. When you forget to delete a heap allocated object and no longer have pointers to it, it's a memory leak. And when you prematurely delete a piece of memory when there are still pointers pointing to it, you have a dangling pointer problem. So premature deletion of memory leads to dangling pointers, whereas failing to delete memory when you've about to lose your last pointer to it is a memory leak. Question 4 is there because many of you forgot on lab 4 to handle deletion properly with linear probing. And that's why I also had a Piazza post before the exam telling you should be familiar with it. So many of you on lab 4 did not stop your search, your find algorithm, when you came to an empty bucket, thus turning a search for a non-existent key into an order n algorithm. Okay, that's not what hash tables are for. Hash tables are for constant time access, which means even if the key is not in the table, we want to terminate our search as soon as possible, not search the entire table. And the way we talked about doing that is that if you have slots that have not been previously occupied and you reach such a slot, you know that the key that you're looking for cannot be in the hash table. So the answer as to why the above find function was inefficient, it was doing a linear search of this table if the key was not there. It wasn't stopping when it reached a bucket that it was empty and had never been occupied. So the solution was to add a piece of code that checked to see whether the bucket had been previously occupied or had not been previously occupied. And we said that that was -1. If it was empty and had not been previously occupied, then we cannot possibly have the key beyond that point. If the slot is empty but was previously occupied, we might still have the key beyond that spot. So an example would be here with 3. It might be that I'm looking for, let's see, 35, I think. Is that mine? No. Let's see. It was a table of size 11. So that one's there. 35 divided by 11. Yes, it's this one. So in this case, if I'm looking for 35, it hashes 35 mod 11 is 2. So we'd start looking at 2. We can't stop when we reach location 3 because there used to be an element there. So it's possible that that element was there when we hashed 35, so we have to keep going, and eventually we find it here. However, now let's say we're looking for 47, which also hashes to 2. We look at 2, 3, 4, and 5, but now when we reach 6, that one is empty and has never been occupied. Well, if 47 were in the table, 47 would have gone there because the entry has never been occupied. So if 47 was in the table, it would have been put into entry 6. The fact that entry 6 has never been occupied means 47 cannot be in our table, and we can exit at this point. So you had to add an if statement saying if the bucket is equal to -1, return -1. Now this else is important. I had the TAs take off one point as a nuisance point to irritate you because you have to get in the habit of not chaining if statements when what you really have is mutually exclusive cases. When you have mutually exclusive cases, you use if-else. And this is a mutually exclusive situation. Either I is equal to the key, or it's not, in which case it might be empty but not previously occupied. But having 2 consecutive if statements is not the best way to do it. It's correct, but it's bad stylistically, and you get a point off for it. Yes? It's still stylistically bad. It's a mutually exclusive, I understand, but it's a mutually exclusive case. And so it's something where if it's mutually, in the future, someone comes in and maintains your code, okay, and they no longer return I. Now you have a set of consecutive if statements. So you can't just be thinking about the fact that your code is fixed in stone. It may be maintained. And someone maintaining your code is not going to look at the code around it. They're just going to look at that one point and try to fix it. Okay? So you have to be cognizant of also what's coming down the road. So if you have mutually exclusive choices, you really need to use an else if. Not just because of what's happening now, but what could happen in the future. I'm sympathetic to what you're saying, but I'm also explaining we need to put you in good habits, okay? So you need to be using an else there. Other questions? Okay. Question 5, most of you got this. So with big O, you knock off you find the biggest factor and eliminate constants. So here the biggest factor, algorithm 1 was n log n. In the second one, the biggest factor was n squared, meaning the first one was order n log n, the second was n squared, and you choose algorithm 1 because n log n is less than n squared for large n. Question 6, you need it just to be able to, this was kind of seeing if you, helping you to see with big O, how it can really make a difference. So you're told an order n algorithm takes 8 seconds. Okay? So an order n squared algorithm is then going to be 8 squared or 64 seconds, a huge amount of time more. A log 2n algorithm is going to be 3 seconds, a lot less. Log n is less than n, which is less than n squared. And you need to become comfortable with log 2n. It will come up again and again and again in computer science. Okay? And 2, 4, 8, 16, you have to be familiar with the lower numbers, how to calculate logs. And there, I knew some of you would not be really cognizant yet of how to calculate log 2n, but I did tell you how you could do it. 2 to the third is equal to 8. Okay. And also you have to do this in your head. If you feel cheated because you weren't able to use a calculator, this is a calculation you must be able to do in your head. Okay? Absolutely must be able to do this in your head. You cannot be using a calculator as a crutch for something like this. Okay? Number 7 was a wipeout question. It shouldn't have been. I covered this in class. It was in the notes. But I'm guessing many of you did not write it down, which is unfortunate. So there's 2 different ways you could delete user phones from the phone map in the Coke problem. One way, A, is that you could go to the user and you could delete, because you're given the user, you're given a pointer to the user. You just iterate through the user's phone numbers. I told you there's fewer than 5 of them, or less than or equal to 5. So there's at most 5, and you can erase from a map in log_n time. So you know or should know that deletion from a map is a log_n operation. This is actually a map. So given that there are at most 5 phones, you know that this is 5 log_n, and since we get rid of the constant, it's order log_n. And we almost always leave off the 2 for log_2n, because in computer science, when you don't see the 2, it's in, the inference is it's log_2n. For the second one, you are iterating through the phone set. Well, if there are 50 million phones, which I said there could be, you're looking at 50 million phones. And while deletion is in fact an order 1 operation in this case, actually it's not. It's still a log_n. And while each iteration typically takes only constant time, because the phone will not match the user's phone, there are still 50 million iterations of the loop for order n. Now, for the up to 5 phones for which you have to do a deletion, it may take log_n time. However, there's only 5 phones that will require this. So it may look like it takes n log_n time, but in fact, it's n plus log_n, and since the n term dominates, the overall time for the second piece of code is order n. Questions about this, because you're going to need to do this kind of analysis over and over and over again in your career. This is one of the most important tasks you do as a computer scientist, is evaluating design alternatives and choosing the more efficient one. And you have to use big O notation to do it. Okay, on the iterator, this was a good problem for most of you. So just quickly showing you how it's done. Pushback, so you start out, puts 45 on the list. Pushback puts 100 on the list. Push front puts 80 to the front. 50 pushes to the front. 200 is pushed to the front. Now we have our X's for our sentinel nodes. We set knit to names begin, so this is now knit. We do 2 pluses, which advance knit to point to 80. Now we set knit1 to be equal to knit, so knit1 is also pointing to 80. We increment knit1, so now knit1 points to 45. Now we erase what knit is, so we erase 80. And knit is now a dangling pointer, actually. If you tried to go through knit at this point, it would be a dangling pointer. But we immediately reset knit to be whatever knit1 was, right there. Now we increment knit again. So knit is now pointing here. Now we do an insert before knit. So 15 gets inserted right there. And knit still points to 100 at this point. And now we set knit1 to be names.end, meaning knit1 points to the sentinel node. So that's your final configuration right there after all the operations have been completed. Okay? Questions on that one? Okay. Finally, number 9. Most of you got the fact that we were creating a circular pointer to new node. Okay, so the diagram that you get, so the first, what happens, we'll do it up here. So we start and we create a new node with Brad. So now we have new node. Many of you forgot the new node pointer, so that was a deduction. You needed the new node pointer. So name is Brad with previous and next. Okay, now we set new node next to be current node. So the next pointer goes up to here. Now we set its previous to be current node previous. So I'm sorry, this isn't Brad. Yes, it is. It's Brad. Now we set previous to Ben. Now we set, and this is the bad statement, current node previous to be new node. Okay, the reason this is bad is that we now lose our pointer to Ben in some sense. Okay, we haven't quite lost it because new node is pointing back to it. But the problem in 5 is we're assuming that we still have our pointer to Ben. That current node previous still points to Ben, and it doesn't. Current node previous right now is pointing to our new node, which is Brad, and therefore Brad next gets reset so that it points back to itself, which is not right. We really want it to have Ben pointing to Brad, not having Brad point back to himself. So there's 2 solutions I suggested. One is to simply swap statements 4 and 5, because what we really need to do is reset current node's previous pointer, which is Ben. If we make 5 go before 4, it will be okay, because then current node's previous still points to Ben, and we'll make Ben next point to new node down here. And then 4 going later is fine. So this was an ordering problem. Better is to create at the outset a new variable called previous node, where you store a pointer to the previous node and can't lose it. And then later in line 5, you say previous node next equals new node. Okay, so basically previous node is now Ben. And so now here it's easy to set Ben next to new node. Okay, some of you did something funky, which is you figured out that current node previous was, just a second, you figured out that current node previous was Brad, and then you figured out, okay, that its previous was now Ben, and so you wrote what is really an abomination, which is current node previous next equals new note. This is unreadable. Okay, your English teacher would have a fit over this. Yes, it's correct. Yes, you lost points. Okay? Please don't write code that looks like this. It is just incredibly hard to read. It is incredibly bug-prone because of that. This is a traversal through 3 links. Okay? It's just hard for a human to get this. It's so easy to mess it up. Okay? So yes, that would be a correction that would make the program work, but it's just incredibly inelegant, and so you lost some points for doing it. Okay? So really, it was an order problem. The solution was to swap lines 5 and 4, or else to introduce, and that my recommendation is introduce an extra variable to hold Ben, or a pointer to Ben. Makes your code a lot easier to read. You should always strive to make your code easy to read. Okay? I'll go over the code examples on Thursday. I need to move on to the Sudoku example because it takes about 30 minutes. And as I said, it's important for Lab 9. Okay? And if you start having an issue with Lab 9, because you really won't be working on Lab 9 on Wednesday, you'll be trying to get Lab 8 done. But remember, I put this lecture up on video. Go to about I think we started around 10, so it'll be around the 35 or 40 minute mark. And find no, it won't, it'll be around the 20 to 25 minute mark. And rewatch what I'm talking about. Because honestly, it probably takes a couple helpings of this lecture to really understand it. Recursion, as I said, is probably the most difficult concept you're introduced to in this course. Okay, whoops, that's still not it. This is it. Okay, so remember, recursion has 3 elements. Okay, it divides a task into one or more smaller but identical, I'll say but similar, because it's not identical, but similar tasks. 2, there is a base case where we can simply solve the task. And simply here means simple. So it's simple to solve the task. Okay, usually this is when we get down to like n equals 0 or n equal 1, where there's only one element left. But it could be a little larger. The example I gave last time was counting coins. When you got down maybe to a pile of 15 or 20 coins, and you had 45 seconds to count them, 15 to 20 coins was probably adequate. So that would have been the base case. And finally, you have a recombination step. So recombine or combine the results of the smaller tasks. Sometimes it's just a matter of returning it. Like in binary search, it's simply you already have the index of the key. In other cases, like in the sort algorithm, quicksort, you had to put the pivot element into the middle of the sorted arrays. In factorial, you had to multiply the result by n. So in the counting example with coins, you had to add up the results reported by each of your friends. So oftentimes, the final step involves a little computation to combine the result. Okay, so last time we gave you examples where either we were dividing a problem in half, essentially, or like factorial, we were dividing it into a task that was one element smaller. So If we had n, we found factorial n minus 1. What we're doing today is considering a game Sudoku. Is there anyone here who doesn't know Sudoku? It's okay to say you don't. Okay. Okay, you don't. So let me quickly. So in Sudoku, you have a panel, a 9 by 9 panel. Okay? The 9 by 9 panel is divided into 9 3 by 3 panels. Your goal is to fill in the puzzle so that in every panel you have the numbers 1 through 9. So if you look at this example solution, you'll see every 3 by 3 panel has the numbers 1 through 9 with no duplicates. Okay? And in every row of your 9 by 9 panel, there can be no duplicate. So every element must be represented once. And in every column, you must have every element represented at most once and exactly once. So you have 3 constraints to your solution. Every row must have all 9 numbers, but no number must duplicate. Every column must have all 9 numbers and must not duplicate. Every 3 by 3 panel must have all 9 numbers and must not duplicate. Now, as humans, we apply all kind of logic to get a fast solution. Okay? You probably have your own tricks, but computers aren't so good at our logic. So one way to solve it in a computer is brute force. Okay? Which is to start at the first value, to start at the upper left-hand corner and find the first one, scan it left to right, top to bottom, and find the first element that does not yet have a number, which in this case is the upper leftmost cell. And you can start by putting a valid number in there. So again, brute force says we start at 1. And the first thing we do is we check to see whether 1 could be a valid number here. Okay, can 1 be a valid number? Yes, because there's no 1 in this row, there's no 1 in this column, and there's no 1 in this panel. So 1 is a potential solution. So we put a 1 there, and using a brute force approach, we now move, scanning left to right, to the next empty cell. Okay, and again, being dumb, we start at 1. Okay, which obviously doesn't work. Then we try 2. Does 2 work? No, it's both in this row and in this panel. And in this column. Goes 0 for 3. Okay, so we can't use 2. Now we try using 3. Is 3 a valid possibility? No, because it's in the row. Now we try 4. Is it valid? No, because it's in the column. Now we try 5. Winner, winner, chicken dinner. At least thus far. Okay, now we go to the next column. And again, I know this seems brutally dumb, but we start at 1. Okay, there are things you could do more simply. You could pass in a vector of 9 numbers and have true or false to say whether or not it's valid, but we're just doing brute force here. We're not trying to be clever. So we'll go through 1, 2, 3, 4, and 5 again. We'll go through 6 and 7. 7's no good. We'll try 8. It's no good. Whoops, 4 is good. Sorry, you're right. 4 is good. See, that's why we use brute force for those humans who can't do it. Okay, and so we go on and so on and so on. Now, this isn't always going to work. You can see from the solution so far that we're clicking on all cylinders. So let's keep going. We got 1, 5, and 4. So I want to get to something where it's not going to click on all 4 cylinders. Okay, so we get to here. And the first number that we can use is not 1, 2, 3, 4, 5, is 6. Okay, 6 satisfies all the constraints, right? So we move on, and the first number we're going to try here is 7, which means when we get to here, what's the number we'll try? Well, we'll try 8, and it doesn't work. So we get up to 9, it doesn't work. So what do we know about this situation? Nothing works there, right? So we have to backtrack. This is an important step in recursion and in game solving, the step of backtracking. So we're going to roll back because to a configuration that might be valid. Okay, we know it's not valid at this point with 7, so we're rolling back and we'll try the next possible number, which is, what's the next number that could work? 8. Okay, and then we'll roll forward. Okay, and we would try, the possibilities are 7, right? Because the only possibility here is 7. Okay? But, and I'm not going to go into it all, we will find eventually, we'll drop down to here next, we'll eventually find out that that configuration isn't a winner either. Okay, I don't know where we'll find out, but eventually we're going to find out that 7 is not a winner there. So then, when we do, we will backtrack, but we'll only, actually let's keep going. So what would we try here first? 3. Okay, so now we go here and we can't try 1 because that's there. Okay, we can try 2, so we're still clicking. Now we come to here, we can't try 1, we're here. We can't try 1 or 2 or 3. 4 is a winner. Okay, now we go here, and what's a winner? 1, 5's a winner. 7, sorry. No, is anything a winner? I think this is where we run out. So we can't use 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're out. So right here, it doesn't work. We backtrack to where do you think we backtrack to? To the 4. So we only backtrack to here. And so we continue with 5, which doesn't work. 6 doesn't work. I think 7 would work. But you get the gist of it, okay? I'm not going to belabor it. The idea is we keep going until we either can get a solution or we backtrack to the previous value. Okay? What we are doing is actually a recursion. Okay, so going all the way back to step 1 is we are filling in one value here. In this case, it was 1. And then we are recursively solving the rest of the Sudoku puzzle. So the recursion is the rest of the Sudoku puzzle at that point. It's the same task with one more cell having been filled in. And we keep doing that, going left to right, top to bottom, until we get to our base case, which is the very last element. If we find a valid value for the very last element, we have solved our puzzle. So if we're at the very last element and we find a valid value, we have solved the puzzle. And we return true, and all of the preceding Sudoku incarnations return true as well to indicate that this is good. Okay, so in this case, the base case, so going back here, divides the task into 1 or more. So in this case, we fill in a cell with a valid value. and recursively solve the remaining puzzle. Solve the remaining puzzle starting at the next cell in left to right, top to bottom order. Okay, the base case is the bottommost, rightmost cell. So the cell in the bottom right corner is our base case. Either we find a valid value for it or we don't. And the combining the results of the smaller task is as follows. If the smaller task succeeds, return true. We found a solution because we have already modified the cell appropriately. Okay? Otherwise, we're going to increment the cell by 1 and see if the next value is valid. Okay? So else increment cell by 1, or increment cell until A, we find another possible value, we find another possible valid value, in which case we repeat recursion, or B, we run out of values, so we return false because we can't, in this case, when we run out of values, there's no valid value for the cell, so we return false to indicate that it won't work with this current configuration. And if we are at the upper left-hand corner and we return true or false, we know whether we solved the puzzle. Now, presumably, it should always return true because the puzzle people are always supposed to give us one we can solve. But suppose some evil genius decided to give out a Sudoku that's not solvable just to tie everyone in knots. Okay, that way you could at least, after banging your head against the wall for an hour, run it through our trusty solver and realize, oh, it's not actually solvable. Okay? And it turns out to be handy. There is a game site called Lumosity.com. Have anyone heard of Lumosity? A few of you. So I enjoy playing it, and they have one game called Pet Detective. Okay, I'll show you Pet Detective. Okay, so the idea behind Pet Detective, you have a matrix, just like Sudoku. Even though this doesn't quite look like a matrix, it can be essentially treated like a matrix. You have some pets, and you're supposed to return them to their homes. Okay, so for example, I can go and I can get the fox and the turtle, and then I can deliver the fox to its home. Now there's an issue. My car has limited capacity. So I might go and get the dog, and then the armadillo, and then the cat. Now I try to get the dog, and it doesn't work because I have a full car. So there's a constraint that I can only carry 4 pets at a time. And you can see that I start with 22 moves. So I have to finish this puzzle in 22 moves. Well, occasionally I get frustrated because it seems no matter what I do, I can only do it with 23 moves. Eventually got frustrated enough that I wrote a brute force recursive algorithm to solve it and verified that in fact it is not always solvable. So they in fact sometimes give you a puzzle where it cannot be solved in 22 moves. Okay, or however many. And it also turns out that once in a rare while, it can be solved with fewer than 22 moves. So I don't know what their generation algorithm is, but I do know that my brute force wonder works, although sometimes it takes 10 minutes. Because this is a fairly easy one, but when you get up to the higher levels, it gets exponential. And it considers a lot of configurations. So at any rate, but the solution was the same. I start essentially with a car, and I go and to each of these go left, go up, go right, go down. And I just do a recursive search until I either succeed or I fail. Okay? So this is a very handy thing. It's often this kind of brute force backtracking recursive search is used in a lot of puzzles. Okay, Dr. Planck, Lab 9, his thing is Neopets. Used to play it with his daughters. Same thing. They gave him a bunch of shapes to solve where you had to, you'll see in Lab 9, you had to apply them to a matrix. He got frustrated, couldn't always find the solution, wrote up a brute force recursive backtracking thing to solve it. So it's nice. A lot of puzzles in this world that are newspapers or on the web, you can actually solve with a brute force recursive algorithm. Okay, so let's see what the algorithm actually looks like. So the recursive, I'm going to go straight to the recursive part, because that's what we just talked about. Let's see, does he even have it? Let's actually go for his solution. Here is his final one. Sudoku.cpp. Okay, so here's his. So his recursive solve begins by calling it with 0, 0. So he's starting at the upper leftmost cell. Okay, then here it is. So he's first going to try to find he's going to find an empty character. And I've set up my grid, so it's a 9 by 9 grid. We're going to use basically an int grid that is 9 by 9. Notice we're not using a vector. Why don't we use a vector? Why are we using a multidimensional array here? Because we know the size in advance. We know the grid is 9 by 9. When we know the size in advance, arrays are more efficient than vectors. So we're using a 9 by 9 grid, and if it's an empty cell, I've set it to -1. So what I do is I'm trying to find here I'm trying to find an empty cell. So while the row is less than 9 and my grid cell is not equal to -1, I'm going to increment my column. So see, here's the column. So I'm going left to right. If I get to the end of the row, that is, if column is equal to 9, remember, because we use zero-based indexing, the valid columns are 0 to 8. So if the column is 9, we increment the row and set the column back to 0. Okay? And we keep doing this as long as our row is less than 9. Okay? So when we're done with this piece of code right here, we either have a cell that we need to fill in, or we've dropped out of the lower right-hand corner. Okay? So we check our base case. If the row is 9, we're done. Okay? We're not able to find an empty cell, which means we have filled in all the cells, and they must all be valid at this point. So if we have gotten out of the loop, we return true, our base case. Otherwise, we have found an empty cell. So we're going to try all 9 values. Remember, we're just stupid. We start at 1 and we go to 9. We set our cell to I. We do our checks, so we need to make sure that the row is valid, the column is valid, and the panel is valid. I'll go through that very quickly in a moment. As long as all 3 conditions are met, this is a possibility. And I call recursive solve now with R and C. Now you might say, wait a minute, Brad. It seems we're doing it with the same cell as before. Why aren't we using R C plus 1? Right? Because I just filled in R of C. I just filled in this cell, so why am I telling it to start the search at the cell I just filled in? Any ideas? It's a convenience thing, which is, I don't know. If I say C plus 1 there, what's the possible problem? I've actually overshot. It may be an invalid C. So I could do a little bit of complicated logic here. Okay, where I check to see if C is equal to 8, and if it is, reset it to 0 and increment R. But then R might be 9, and which means that the recursion is done. So it's just simpler, it's more elegant to just call recursive solve with the current cell. And why is that? Because, whoops, darn it. Come on. Because when I back up here, I know that I already filled it in, so this logic will take care of it for me. So I'm just basically, passing the buck to the next recursive call, and it will do all the checking to find the next cell to fill in. I know for a fact it's not going to try to fill in this cell because I just filled it. It's not -1 any longer. So the reason I do it like this is it's just a buck passing thing, so I don't have to repeat all the complicated logic there. Okay, so if I'm unsuccessful, I need to reset the cell to be empty so that I can backtrack. I failed, so it's set it to empty and return false. So I know I failed if I fall out of this loop, because if I succeeded, I return true. If I ever found a good number, I succeeded. So if I don't, I fall out of the loop eventually, having tried all 9 numbers. I know I failed. Okay, so it's actually a very elegant algorithm. Okay, and these 3 checks are pretty simple. The rest of it is reading in the grid and doing the checks. So just quickly, I'm going to let you read the rest of it because I think you should be able to do the rest. It's pretty simple. Reading in the grid is simple. Checking for validity is pretty simple. The one So for example, let's see, going back to the top, he is keeping his grid. Well, he actually kept it as a vector. I didn't. Should be. Oh, wait a minute. Wait, what? Wait a minute. Maybe I have to change that. Mine was using a grid. I may have, well, no, he's using 9. Okay, I'm going to recheck it. You really should be using a 9 by 9 integer grid here, but he's using a string, so be that as it may. I thought I'd rewritten these notes so it used a array, so I'm going to go back and check. Let me just check this quickly. Yeah, okay. So my solution, I'm using a 9 by 9 integer grid. So I'll go back and change that in his notes. But the interesting thing here is checker. So you'll see that whenever he's checking row valet, column valet, panel valet, what he's going to do, I'm going to go over it by a moment, but not for long. So he's checked for a row valet. He's going to go through and he's going to say, he's going to look at his, he's going to go from 0 to 9 and he's going to set his checker thing to 0. This is all wrong. Why is this? It's like, okay, I'm going to have to check this. This should be true, false. At any rate, he's setting it to 0. Then he is running through for I equals 0 to 9. So if it's not an empty cell, which he's denoting as a dash, I denoted it as -1. He then checks to see if that number was already used. Okay, so if it was, it's not a valid row. If it wasn't, he now indicates that that number has been used by setting it to 1. So checker is true, false. 0 means the number hasn't been used. Checker 1 means it has been used. So he's basically just going from 0 to 9, checking to make sure that that hasn't been used yet. And he returns 1 if it is a valid number. And the reason he uses this as an instance or as a member variable rather than as a local variable, this is important, so just take a moment. The reason he uses it as a member variable and not a local variable is because it is very inefficient to always allocate and deallocate either an array or a vector. So he's going to call is row valid, is panel valid, is column valid many, many times. And it would be inefficient for every function call to always allocate the same 10-element array or vector. So instead, he simply makes it a member function variable, meaning it's only allocated once. And then every time through it, he is resetting all the values back to false, which is something that would be done anyhow by a vector thingy. Okay, by the constructor for a vector would also set everything to 0. So in this case, using checker as a member variable is more efficient than always allocating a array or vector as a local variable. It's just a cute trick to put in your memory banks, okay? We wouldn't take off for having declared checker right here as a local variable. Just explaining why he did it. Okay, I'll see you all on Thursday. Explain the relevance of all of this to Lab 9. And